welcome everybody. We're going to get started. I hope everybody has managed to find a seat. Great to see so many people show up in great numbers. We have a special visitor here today, which is Professor Stefan Thurner, who is a professor in the Medical University of Vienna and director of the Complexity Science Hub in Vienna, which has all to do with complexity science, complex systems. And we're very happy that he will give a talk for us today towards a statistics of complex systems. So please take it.
Yeah, thank you very much for having me. And sorry for the, it's morning, still morning, and statistics is maybe not the most sexy topic, but I'll try to do my best in showing you an exciting glimpse into a statistics that many of us thought was not really possible to do. A statistics for systems that are driven. And yeah. Okay. So where does statistics come from? If you go back to 1809, that's the year when Gauss first conceived the idea of statistical errors. And yeah, he understood that if you add up random numbers, the sum of the random numbers looks like a Gaussian. And a year later, the French did it, of course, better than the Germans. Laplace, he really formulated the central limit theorem more or less in the way that we know it, that we know today. And saying the same thing: the sum of random numbers, if these random numbers come from this the same distribution, and if these random numbers are not correlated, if they are IID, identically independently distributed, then the sum of these random and if the variance of this distribution is finite, then your sum will be, if the sum is infinitely long, is going to be a Gaussian. Yeah, that's true for
recording in progress
for independent and non-interacting simple systems. And let's talk about the Gaussian for a second. Gaussian is a nice thing because if it's an exponential, something that's growing very fast, to something negative is going down to zero very, very fast. And if it goes down quadratically with the argument, if you look at if x here is 1.36 something, if x is 10, it's already a really, really small number. Yeah. Just to make sure we are all on the same page, this is a power law. This is an argument to a negative power. If the argument is 1, then it's 1. If the argument is 10, it's 0.1. So there's 40 zeros less. Power laws are incredibly slowly decaying. Yeah. If we have a complex system, most of the time when we talk about complex systems, we have something in mind where we have elements, and these elements are connected to each other through networks. If one element changes, it will, through the network, also influence others. We won't have an independent situation anymore. We have correlated situations and maybe very complicated interdependencies. We have more than one source of randomness in complex systems. If different elements feel different sources of randomness, we have many sources of randomness. And also violating the central limit theorem. The statistics of complex systems is to a large extent the statistics of power laws. Yeah, I'm preaching to the converted, but what I said before is that these power laws, and this is so slowly decaying, complex systems are characterized by outliers. You have a slowly decaying probability distribution. Outliers are dominating the statistics, and that's one reason why we call these things complex systems, because the outliers are so frequent. So power laws really are pests. Why? Because they're everywhere. They're hard to control. You never get rid of them. I'll show you a couple of examples. If you look at the city sizes, we see a power law for those who are not familiar with double logarithmic plots. If you're plotting some distributions in double logarithmic plot, if you see a straight line somewhere, that's the power law. Very often you have shoulder here in the lower part, and then in the tail we have a power. So cities are distributed, city sizes are distributed as power laws. Rainfall events, if you look how much water comes down in rainfall, these are power laws. Landslides, maybe not the most important thing in the Netherlands, but in Austria we have landslides, these are power laws. Damages caused by hurricanes are power laws. Financial interbank loans are distributed as super nice power laws. Forest fires are in different regions. You see that there's power laws. There's moon, that's super relevant. The moon crater size distribution is a almost perfect power laws. There's here behind the green ones. We come back to this, why this has to be. If you look at the energy distribution of the gamma rays from the sun, the power law, it's not exactly a power law, you have maybe a little bit of an exponential cutoff, but it is definitely not the Gaussian. What would the Gaussian look like? Would be like something like this, would look like a parabola in a double plot. Movie sales, healthcare costs, in particle physics, certain cross sections, if you extend them far enough, you find power laws. Word distribution in books, that's maybe the most famous power law in the humanities. Zipf's law. If you suffer from insomnia or read bad literature, what you can do is to start count words. How frequently do words occur in a book? And then you can do if you're really sleeping bad, you can say how often is the most frequent word occurring. Plot it here. The second most frequent word that appears in English, it's that. That occurs this many times. The second most frequent word appears half as often as the most frequent word. The third frequent word appears a third as often as the most frequent word. And the 100th most frequent word appears as the 100th of the frequency of the most frequent word. That's Zipf's law. It's a power law with a slope of 1.
So this is checked for different languages or for English?
Oh, no, it's for letter-based writings or texts.
Not Chinese.
Not Chinese.
It's really also specific, right?
It's a little bit author specific. There's lots of
People can actually distinguish text from author.
Yeah. Not only from
Yeah,
not exactly from the exponent, but from
Variations.
from nestedness, which is not exactly the exponent, but it's related. Citations of scientific articles, power law distributed. Website hits are very often related to search processes. You search something and then you, we'll talk about this.
One question about the word distribution. Did anyone look at ChatGPT?
Good.
To see if maybe that's the way to distinguish it from real text.
I'm sure it will follow. It's so good. And it can't do this one wrong. I don't. Telephone calls, earthquake magnitude, that's Richter's law. You all know since high school. Seismic events, that's Maury's law. What's the aftershock distribution? War intensity, killings in wars, sizes of wars, wealth distribution is a famous one. Family names in telephone books in the US. And we haven't talked about all of these things. We did not talk about networks. There's hundreds of degree distributions that are more or less scale-free or power law. We didn't talk about allometric scaling laws in biology. There's dozens and hundreds of these power laws. If you look at dynamical variables in cities, if you look at fragmentation processes, correlated random walks, certain noise process in technological contexts, blackouts, fossil records, bird sightings, terrorism. It looks as if Gauss has never lived. So, where do we see Gaussian distributions? Yeah, in physics, in some really specific things, and in some non-complex systems or very simple systems where things are really uncorrelated enough.
Stefan, isn't it also because you don't sum up things? I mean, the CLT you sum up things, and here it's not like the spread of something that is not inherently.
So very often we are summing up things here too, but there is usually through the networks you're summing, double summing, triple summing the same thing, and that leads somehow to these power laws. But I'll show you something very, very clear and precise how to get these power laws. There's a couple of traditional rules since the central limit theorem breaks down. Is there something like the central limit theorem? That's a question. There's not such a thing. There's different routes towards understanding power laws. One is criticality. Physicists have worked this out in the 1950s to 1980s. Self-organized criticality. So criticality has to do with the physics at phase transitions. There, things become power law distributed. Self-organized criticality is a situation where these critical parameters the system finds by itself. Very, very nice. Multiplicative processes don't lead to power laws. If we are multiplying random numbers, what do we get? We get a product of random numbers.
Another random number. Another random number.
That's another random number, but what's the distribution? Here's an answer.
Oh, no, I actually, can you move the Zoom button?
Should we log normal, I guess?
Log normal. Why? Because if we take the log of this product, it's a sum of logs. And if we're summing random numbers, if the variance is finite, it's a Gaussian. Yes.
Now I have something about the slides. Just a quick question. So you're going to mostly talk about sufficient conditions, but we will also talk about necessary conditions. So we definitely know that for something that will generate power law again, that is a prerequisite, right?
Yeah, I'll talk about necessary conditions. And we can know that would be the nicest thing, to have the sufficient thing at the end that would close the bag. And towards the end, I'll show you that we can close the bag a little bit more, but not yet,
Maybe
100%.
you don't know the mechanism, but this is resulting, what's the name, stream value theory, where you get these three distributions that would also incorporate large tails.
Say it again.
Do you consider this an extreme value theorem?
Extreme value theory.
Yeah.
Yeah, is related.
Yeah.
Wait till I come to the point, and then we discuss what is all related to to what I want to say. The last classical route to explain power laws is preferential processes, rich get richer phenomena, self-reinforcing processes that traditionally also lead to power laws. We didn't finish the multiplicative process, so we get log normal distributions. If you put constraints, pretty harmless looking constraints on a multiplicative process by saying the sum of all random numbers should always be 1, something like this, or you cannot go, or your lowest, there's a lower threshold for your random numbers cannot be lower than X, then you get exact powers. That's something very nice. Sometimes we have one phenomenon and 4 or 5, this is the problem, 4 or 5 explanations for it. So the Zipf law in word frequencies has been explained by preferential attachment rules, completely unrealistic situation. It tells you a word is used as frequent as it has appeared already in the text. That's exactly what our language teachers tell us not to do. And Mandelbrot came up with a constraint optimization thing involving entropies. Miller came up with a complete random text generator. That's maybe the most brutal way, and Ricard Soleil has an improvement on Mandelbrot's view. I'll show you yet another one and yet another one. So is there a unique principle? Is there something like necessary and sufficient conditions? Is there an equivalent to the central limit theorem? Let's give you a second motivation. When we talk about complex systems, most complex systems are not equilibrium systems. They're driven in some way. You're putting in some energy, the system does something, redistributes the energy, operates according, and some energy goes out. Or you put in money, or you put in goods and services and run through the supply chain, and something comes out again. Systems are almost always driven, except for economics. There, everything is in equilibrium, and that's why we're sometimes off. A driven system has a driving part. Sorry for these trivialities. A driving part and a relaxing part. So driving means putting in energy, exciting maybe the atoms or the parts in the screen. And relaxing is the thing when I turn off the input, thing goes to lower and lower states and relaxes, and then usually stops working at some point, goes to a ground state. Yeah, that's I'm saying this now. At the 10th time, it would be nice to have a statistics for driven systems that are not in equilibrium and explain at the same time the abundance of powers. Many complex systems are also path dependent, meaning that their history determines the probability for being in the next time step in a particular state. Yeah, that's also clear. And so the sample space, the possibilities that are possible in the next future step, the adjacent possible, if you want to use a heavily used word, depends on the history of a process. I'll show you a driven process now. We call them sample space reducing processes. These are the processes that relax. So if you think of having dice with different numbers of phases, and I have the process that I start with the die that has 13 phases, I throw it, and whatever number it tells me, I then go, if it tells me 9, I go to the die with 9 phases and throw this one. I can get a number from 1 to 9. I get 7, then I take the 7-phase die, throw this one, and I do this until I get to a coin, and then to a die that always gives 1. That's a stupid die. So then I repeat this process, do it again, do it again, do it again. Then I ask, how often do I get the numbers 1, 2, 3, 4, 5? What's the probability distribution of getting numbers in that process? It's a sample space reducing process that's repeated. What's the repetition? The repetition is the driving. Okay.
Just to be sure, so is this equivalent to fragmentation process where
Very close. Yeah, yes. This is. I come to a process of breaking spaghetti at the end, or meteorites. It dates back to Richard Feynman, the spaghetti breaking process, yes, fragmentation is such a process. Here's an example of sentence formation. How do we produce a sentence? I can open the Oxford Dictionary, pick randomly a word. So this is my dictionary, I pick a word randomly, it's wolf. As soon as I pick a word, I can no longer use any other word. Why? Because we have grammar and we have context. Grammar forces me now to use a verb. Doesn't force me, but I should use a verb, otherwise you'd think I'm an idiot. So I choose a verb, and this cannot use any verb. It has to be compatible with a biological thing like a wolf. So context forces me. As soon as I'm creating a context here, it reduces my sample space further and further until I come to the point. And the sentence ends. Then I do the next sentence. The next sentence, I start again, I'm driving the system, and then I do it again. If I do this repeatedly, how often do I get the different words? That would be the Zipf law. Let's see if this comes out. Here's yet another depiction of the same thing. We have different states. The states have different levels, energy levels or whatever levels. And we have a ball that can roll down, hop down random distances to the left, but never up. Once the ball is down there, we bring it up to a higher state, randomly, for example, and then it falls back down. That's the driving process, that's the relaxation process. If we do that, how often do we visit 1? Very often, because it always goes to 1. How often? 10? As often as we start the thing at 10. This curve is Zipf's law. The probability of finding state I is 1 over I. I is what? I is 1, 2, 3, 4. That's the index of the states. So why is this? So don't want to bore you, but the probability to find the ball at the state I is the probability that now it was previously at state J, which is higher up, times the probability that it goes from J to I. What is that? It's, in the simplest realization, it's 1 over where it now is.
Sorry, what does SSR stand for?
SSR, sample space reducing. So over time, the number of possibilities on average get less. Yeah, if you plug this in, you get this equation out. If you do the same thing for probability I plus 1 for the next state, you get same thing, just you increase I by 1. If you subtract this state I plus 1 from state I, you get this relation. The sum drops out. We do this, and this is if you realize that these are differences, you see you can take the log, you can solve this, and P, the probability of I is I to the -4. It's not more complicated.
Of the driving process, so this is of the just initialized one.
We initialize it one, no, we drive it.
Yeah, but you don't see the driving process here.
The driving process is one over.
Okay.
Once it's down at state number 1, it's with probability 1, I put it to a higher state.
I think is there a crucial assumption that there's symmetry in the probabilities?
There is an asymmetry. This is in technical terms, we are breaking detailed balance. So the physicists know what I'm now saying. I'm doing something very, very, very bad. No one is breaking detailed balance. But this is the soul, that's the origin of this power law. Yeah. So there's an alternative proof. We had
System do it all the time.
and more complicated proof earlier. Yeah, so why is it interesting to have the visiting distribution of states in a statistical system? If you have the visiting distribution of states, you have a statistical description of the system. Yeah, so that's why we're doing it. It's quite a lot if you know that in a complex system. Now you can say, this is a special case. This is a particularity, not very general. This is I needed a long time to explain it. This sample space reducing process. What, for example, happens if I don't wait till the thing is fully relaxed, but with a certain probability I restart from any position again, or if I, with a certain probability, kick up the ball. If with the probability 1 minus lambda, lambda being a number between 0 and 1, I kick up the ball to a higher state, and it's a higher state, I get another relation, still a power law. Probability of finding I is I to not -1, but lambda. Lambda is 1 minus the driving rate. You don't believe me? We prove it. I'm not going into it, but it's the same eigenvector equation. Plugging in what I just said, getting in some relations where you realize logs, and then this is exact. So it should be in both sides. It also works if you don't have if you have not discrete states. Continuum, it also works. Will work to show it. Yeah, so yeah. If you still don't believe it, you can do a simulation. Just do a five line code. If you have no driving rate, you wait until the system is down to the lowest state. You get a power law with slope -1. If your driving rate is a little bit higher, 0.3, you get this slope. If it's 1/2, you get this slope. It's must be like this. Let's generalize a little bit more and now it becomes non-trivial. If we have prior probabilities of visiting states, we're sampling these states with a ball that hops left and right, we would get the prior distribution. We could recover the prior distribution. if we have a sample space reducing process where we have this tendency of the ball going to the left side, what do we get? We get Zipf's law. Unless we are overdoing it. If we have this, if we would have exponential distribution of these prior distributions, it would no longer work. But as long as this is power law or polynomial, it recovers Zipf's law, exactly Zipf's law. That's, if you don't believe it, here's the prior distribution where you can put this in. Nothing gets more complicated than this. Maybe you need a page, but for polynomial priors, you get Zipf's law. Lambda being the driving rate. Okay, so the prior probabilities are practically irrelevant. That's a big statement, and you would not intuitively make such a statement. So we have relaxations. Yeah, I think I made that clear. The relaxation part is the sample space reducing process, and the details of the relaxing part in the process do not matter in the statistics. Also, if you take out many states, that does not change the situation.
In this example, where you have the sample space reduction, so if you allow for like a small random probability or maybe exponentially distributed probability, like noise of hopping back up, does it still work?
That's what we do. That's this lambda. This is the noise with which you hop up.
Oh yeah, that's the
But you hop up,
That's a driving.
you hop up completely to the top.
No. You can hop up and just to a higher state than you are currently.
but the exponents that you get out will always be smaller than one. Or
Yeah, it will be smaller.
There
We
are-
come to that point of
that are
exponents bigger than -1.
That's
But smaller than
the
-1.
bound lambda between 0 and 1, right? So,
The lambda now is between 0 and 1. Now we're just talking about slopes between 0 and -1. We'll see in a second what kind of processes will give different slopes. Okay, if not all of these transitions from I to J exist, what happens then? Then we have a situation where we have diffusion on a network. Yeah, that's a network telling us from which node I can hop to what node. And let's look what happens if we're looking at sample space reducing processes on networks. We can take such a process, put the states here, and then just draw a network of which hops are possible and which are not possible. Here's the relaxation part, here's the moving up part. And what is such a network called? It if you're just looking at the relaxation part, this is an acyclic directed graph, or directed acyclic graph, DAG. So an acyclic directed graph is a graph that has some kind of order, and if you want to direct it, you go from higher nodes, draw direction from higher, for example, to lower nodes. Now it's a directed graph. It looks as if it has cycles, but they are not. The cycle has to go in one direction only. So this is not a directed cycle. Yeah, it's a directed acyclical graph. Now, if we put random walkers on there, it can only go to lower states. It's a sample space reducing process. It's diffusion process on such a graph. Let's take a random graph, for example, put these random walkers, put some order on this, have random walkers. Let's look what is the visits, how often are state nodes visited. We see Zipf's law. Okay, little bit remarkable because we don't have any transition from everyone to lower states. Now it's much, much sparser.
And is there a restarting in this process, diffusion,
Yes, there's a restarting that we keep putting random workers randomly on the nodes.
And does this law depends on the density of the network? Or you need to be sparse?
If it's fully connected, I've shown you the situation before. Now it's just a sparse. This is to show you that it also works for very sparse situations.
There's no variability no matter the.
It doesn't matter. Everything in between is possible. If we take another topology, exponential network, completely different thing than an Erdős-Rényi graph. Zipf's law. If we take a completely crazy network, the co-authorship network of high energy physicists, and put random workers there, you also see Zipf's law. So the prior probabilities are irrelevant. It's the same statement as before. Now, if we introduce weights on the links, so for every link, the equal probability that someone jumps, if we put weights that reflect the probability of a jump, if we put, for example, I don't know, Poissonian weight distribution, we get Zipf's law. If we put a power law weight distribution, something completely different, we get Zipf's law.
But there is a deviation at small values.
Yeah.
What's the cutoff?
So, yeah, the shoulder, we're that's from the details from this.
What is figured out, like what's the cutoff of deviation?
Yeah, this is perfectly under control.
but there's one, so instead of in the graph you showed before from data, it actually was always a shoulder that was, but here it seems to drop down first and then has a kind of. So there is this top left, there is this at the y-axis, there is this high dot. Both in the Poisson weight and
This one?
yeah, and in your Poisson weight and your the previous slide with the different weights.
There was this shoulder.
Yeah, but there is
And
always
it's high one.
and that high one, yeah. So which was missing from your
And I'm missing the x-axis
yeah,
and
but it seems to be
maybe-
like more like this than what where in the beginning of your talk the shoulder was always flat basically.
Mhm. Yeah, no, this is something I should look up.
Yeah.
If this is now one, or if it is the.
But what you get on the left will depend on the driving process, I guess, and what you get on the right.
Now let's come to this. Here is just a random.
Just from my understanding, when we look at power laws, we are only interested in the tail, right, and not in the.
Most of the
left
time.
part.
The left part is usually due to details and that's it.
So you don't want to have, well, I don't think you should impose on your theory that it also matches the left part. I think only the right part as well, right?
The story is about the right part, the emergence of the, but we also understand why the shoulder is there, in this case. Now, if we make the acyclic graph cyclic, we allow cycles, directed cycles. What is this? If we have a cycle, we are from time to time jumping from a lower state to a higher state. That's the faster driving. That's introducing this, making this lambda larger than 1. Yeah. So if we introduce these cycles, then we're changing the slope. Why? Because it's the driving, the number of cycles corresponds 1-to-1 to the driving rate.
So the fraction of cyclic graphs is now 1-2, right? In the left graph. Lambda was the probability that you went down basically in your
1 minus lambda is the driving.
1 minus lambda is the
Yes,
driving.
1
yeah.
minus is the lambda.
Yeah.
Yeah. So with the slope of the visiting distributions in a directed graph, you can measure the cycles. kind of nice, no?
Very nice.
So, yeah. So to summarize, no matter what the network topology is, you get Zipf's law. No matter what the weights are on the network, you get Zipf's law. And if you have cycles, the exponent is the number of cycles, or corresponds to the density of cycles. Now, a couple of examples of sample space reducing processes. A search process is if you do good search, it's a sample space reducing process. I'm looking for my keys and I'm looking here and looking here and looking at the same spot is idiotic. It's bad search. With every spot that I search, I exclude possibilities. That's sample space reducing.
Is there some noise? Because it's true that biological system also reduce the sample, but they need some noise to a bit explore that they are not stuck in one region of the space.
The noise is this driving rate.
Okay, sorry.
Yeah. You can also formulate or run the system that with this driving rate, you're hopping upward. That's what I've shown you, but you can just hop to any state. Then you still get the same results. And that would then be really noise.
Thank you.
Now, if you click on web pages, very often this is a result of a search process. So if we're looking, this is one of the first papers that ever studied click rates. You get, if you do the distribution, how often websites are visited, you get more or less Zipf's law. If you're doing, this is all of the internet in 2002. That's ancient times. Also ancient times, if you do professional search, if you're working at a tech company and you're looking up for a specific, I don't know, patents or for part of algorithms, and if you look how your people are searching for information on in your corporation or something, this is different corporations, different companies. This is how their employees are looking for information on the websites internally. It's always exactly Zipf's law. It's not our data. And again, see, this is ancient, and from day one, this holds. Now, what about exponents larger than 1 or less than -1? If we have this staircase process, we have a ball, but before it jumps, it multiplies. Yeah. Multiplies by a factor mu. So if mu is 2, we always double. If mu is 3, before jumping, we would triple. And then just everyone is doing the same thing. Then you can show half a page. This is the distribution that comes out. Mu, the multiplication rate, is the slope of the state visits.
Do both copies jump?
All copies always jump. As soon as it's created, they all go down the staircase.
What happens if one stays behind?
Huh? If one stays behind, that shouldn't happen. then something.
I'm a biologist. You have innovation processes and immigration. So, like, somebody stays behind. Then,
Yeah.
So that's.
Yeah.
Yeah.
Okay, so we did not say that.
Yeah.
The question is how it's brings maybe some bump or something. Yeah.
So if you don't believe it, you can do a simulation. You will find out that this is the case.
So if mu is fractional or like rational number, that's the probability of.
Yes. If we introduce a conservation law, that's what physicists do. If we are splitting a particle into 2 particles, the energy should be the same, should be conserved. So then this would be a hadronization process, for example. You know, all of the hadronization process is a particle with high energy has enough energy to split into two particles. And then these particles still, if they have enough energy, they can split into and a certain Italian Enrico Fermi, who was known in the 1900s,
No, weiß weniger.
figured out what is the energy distribution of the cosmic rays.
This is the parable you showed at the beginning, no?
No, I haven't shown it yet.
You showed cosmic rays.
Yeah,
Yeah. I showed no, it's not the cosmic rays, it's just the gamma particles from the sun,
Okay.
which is part of the cosmic rays. So now we say if we introduce a conservation law, that the energy of the two resulting particles must add up to the energy of the original particle. We impose that. And we can do a little bit of algebra and find that the probability of the states with this constraint is always -2. Always. Yeah, it's just the outcome of math. And the 2 is Fermi's result for the cosmic radiation. Now, people typically, if you're a physicist, you become aggressive, say, Fermi was doing physics and all understanding everything, and you're not doing physics. This is just numbers and statistics. No, we did physics. It's the conservation law. That's the physics of it. And thank you for not getting aggressive. Yeah.
Is
another.
Sorry, there's a question on the previous slide, because in the case of the multiplication, the exponent that you got was minus mu. If you have a multiplicative factor of mu, the probability was going to I to the minus mu.
Yes, and it can be now we can explain slopes from 0 to minus infinity.
And in the case of the Fermi case, like there was a multiplication of the mu was 2.
No, not necessarily. In the cosmic rays, one particle can go into 10,000.
Okay.
But if you have the energy conservation, then you get the 2.
Okay. So any factor in that case, but
Yes.
only conservation.
Yes. So we don't have to do the nitty-gritty stuff that Fermi was doing, going through the possibilities that you can have. None of this is necessary.
So constraints, they have an influence on the exponent.
Yes.
And does that work for other constraints, like energy conservation?
I don't know. Here's another.
Can I ask another question on the? Sure. So in the case of the dice that you roll, and then so what it means is that when you roll a dice and let's say you start from 13 and you get 7, you keep both a dice with 7 and one with 6. So it's like you split the two. So, or it's a different thing.
No, I have all these dice on the table.
Mhm.
And I'm just, and I have a list of numbers that appear on the dice. I start with the biggest one and throw it, and whatever number it gives, this is the next die I will pick up. I'll not split, and I'm only recording the numbers that appear.
Yes, this is the starting one, but when you impose energy conservation.
I don't know how to impose energy conservation on this. We cannot. We can only, if these states are energies, then we can impose energy conservation.
But you showed in the previous slide this result, but so what is mathematically the conservation law that you have? You have some kind of
How do you predict the two?
The conservation law is that whatever the energy, if F is energy, can be something different. Energy of state 1 plus energy of state 2, and how often you multiply it must be, that's the conservation law. Whenever you put such a thing in, that among all the sequences you can get, you have that constraints. Yes, you're reducing the number of total sequences drastically through that constraint.
And this does not depend what your function f for.
No,
That's
no,
independent.
Also exponential.
And therefore,
that's not a function, that's just the characterization or the dimension of of how you characterize your state. So don't think of this as an exponential function or log or something.
Is this still with the driving?
You also have to drive these, yes, if you're only taking one, you get one sequence down and then you cannot do
No,
much of
sorry,
statistics.
The drive, like the noise driving up.
This here is for the slowly driven situation. So with the lambda of 0. So here's maybe the last example I show. It's a classic problem that physicists gave up on working on. It's a box. You have particles in the box, and then you let these particles collide. What is the energy distribution of these particles after they have collided a couple of times? All of you will say it's the Maxwell-Boltzmann distribution, or the Boltzmann distribution, and end of story. But what if these particles are not colliding elastically? It's only if energy is not dissipated at the collisions that the Maxwell-Boltzmann distribution holds. If you have a box with inelastically colliding particles, what is the energy distribution?
it's very popular, I assume.
No. No, completely wrong.
All get the same energy.
No one knows. No one. People have worked for 100 years or 150 years for the left part of the distribution. There's a little bit of understanding there because it's close to the Maxwell-Boltzmann. In the tails, they know it's power laws. But the whole distribution, no one knows. There's of course been simulations for that. Since 20 years.
In that case, the distribution is not going to be time invariant, right? Because there's dissipation going on.
Yeah.
So you cannot talk about the distribution.
You cannot get it to the state.
At least not invariant.
No, wait. We want a stationary situation.
Right.
And since at every collision we're losing energy, we have to reintroduce energy. We have to drive it. Bravo.
Also the goods. Okay.
Yeah, so then we have different methods of how we can do this. What would a physicist maybe do at the border? If the particle hits the border, then you get the energy kick because you get the heat. Or you could shine a laser in, randomly you kick particles. You
Shake and
introduce-
granular matter, maybe.
Huh?
But people in granular matter, they vibrate it, and they
On
are
the floor,
exactly
yeah,
inelastic
right.
because they are frictional, the grains.
There's different ways. And what you have to do is to compute the transition probability from one energy before the collision to the energy after the collision. You have to put in the collision process. Oh, thank you. This is very, very valuable. It's tedious, keeping track of these angles and then integrating them out again. But it's fun, like it feels like first semester. And you can write down this energy distribution. You plug this into the eigenvalue equation that we had before. And we have to put in the driving process. I don't see now. See it here. No. Is that the driving process? the driving process is inside of this transition. And why did no one compute this yet? Because everyone knows this will depend on how you put in the energy, on the details of how you do it. It depends on the geometry of your box. And it depends on the size of the particles. So what do you expect? But now we can plug this equation in. We cannot solve it analytically, but the computer gives us the solution to this eigenvalue equation. And we can overlay it with simulations. And we almost get a perfect situation. This is the theory. This is the exponent in the tail. So this is just one part of the distribution. The exponent in the tail is computed by this eigenvalue equation, and the dots is the simulation for different inelasticity coefficient for different sizes of particle sizes, and we even try to see when the dimension of when the shape of the box starts playing a role. It's the least influential role. Okay,
Could you please explain the one before that? You had a theory above and simulation.
Yeah.
Oh, yeah. So what are we looking? Because in the bottom.
Yeah, we're looking at the blue curve.
Yeah.
Is the Maxwell-Boltzmann distribution. Right. If we have this inelasticity coefficient 1, elasticity coefficient or then we get this blue curve. As soon as we change this a little bit, we get this power law tail, but it's not a power law, it's more than a power law. The power law, maybe here another power law. Here's the driving energy. And this is what the theory gives us. This is the solution to the eigenvalue equation with different internal energies.
And you then look at the slope before you look at the.
We don't look at the shoulder.
No. But you in the theory in the next slide you actually look at the slope of these curves above.
Then we take these. And this we compare. Yeah, we also compare these as possible.
Can you show once more the analytical formula with the right?
So this is the transition probability for given inelasticity coefficient that you plug into probability of finding the particle in energy E, that's the energy distribution, is equal to the probability that the particle is in a different energy. E1 without the prime, and you multiply with this and integrate out all the variables that you get all possible collisions.
So basically you can simplify this full solution at some limits to get the power law at the large E. Yeah, that's what you did too.
So we did not, when we plugged this into the eigenvalue equation, we were not able to solve this analytically.
Okay.
But we let the computer solve it.
Okay.
And
but in some
solutions are these curves.
In some limits you cannot solve it, like for some because
some limits.
Some large E, for example.
For super large E,
yeah,
you can solve analytically, but there's huge confusion in the literature. Different groups have done this over the last 30 years. And sometimes they are looking at this, sometimes they are looking at this. They don't know exactly where they are.
The window is right, window is.
Do you know whether these two branches are also power law, or we only focus on the big branch?
Yes, these are
There are true power laws then.
True power laws. I mean, look at the orders of magnitude. In the approximations, they turn out to be in the analytic work, they turn out to be true powers. Yes. Yeah. So last thing, what if your driving rate depends on the state you are at? So far, we have had a very homogeneous driving. Just it's one number, it's a driving rate. What if the driving rate depends on the state? If you're at lower states, maybe you drive more. That would be a self-organized system, critical system, maybe. If you're higher states, you drive less. And let's say this lambda is just a function of k. K being what I called I in a different paper. If we have this function, if we plug this function in now, we do the same kind of eigenvalue equation. I didn't put the eigenvalue equation, but here's the transition probability. This we plug in the equation, we get this result. And what is the final story? The driving rate is related to a pretty simple formula to the distribution function. I told you that the details of the relaxation did not matter, but the driving matters. So if you have now, we can look at different driving functions, state-dependent driving functions, and look how this influences the observed distribution functions. Let's do what we have done already. If lambda is equal 1 constant, if we take the if we divide this x over there, integrate and take the exponential, we get Zipf's law. If lambda is another function, another constant, not 1, but a different function, you do the same thing again, you get the distribution function is an exact power law with 1 minus lambda being the driving rate. That's the same thing that we had before. If lambda is a linear function in the argument in x, this is an exponential function. If we have lambda, a constant plus a linear part, we get what people call a gamma function. And this is this power law with this exponential tail at the end, which we have seen maybe 15 times in the plots I showed in the beginning.
Yeah, I was just curious if you have more example. Maybe you answered my question.
We get the Gaussian. If it's a power law, we get the stretched exponential. If we have a log in there plus constants, then we get the log normal and so on. Yeah, so you can one-to-one, if you know how you're driving the system, you know if you have a sample space reducing or a relaxing process that you can describe with a sample space reducing process, you can predict what your observation, what you expect to observe.
Are all these functions, are all these lambda functions increasing functions of x?
Yeah, but not necessarily. You can also decrease in x.
What if the function is more a stochastic process?
I don't know.
Because
Yeah, I don't know.
from
Good question. Okay, so to wrap up, maybe.
That last slide connect to the extreme value theory, I assume, because it's theorem that only 3 distributions are the distribution of the tails of any data. Is that the connection?
So the example that one-to-one relates to extreme value theory is record statistics. If you have a time series and you ask at every time step, is this the value in the time series now a new all-time high or not? Then you get this curve, how long you have to wait to see the next record on average, right? This record statistics, and as soon as you have a new record, you're reducing the sample space for the next record. So in that sense, you can, we've never published it, but we have finished the work, relate record statistics one-to-one with this sample space reducing processes. So just to sum up, what other systems are of this sample space reducing nature? If we have self-organized, so any driven system that lead to stationary distributions should be part of this. Again, this is not yet not at the quality of a sufficient condition. Any self-organized critical system is a sample space reducing process. If you think of sand piles, for example, you're putting sand on a pile, and it gets too steep, then you have an avalanche going off that reduces the slope. That's sample space reducing. Super complicated to keep track of everything. That is hard. It's not that you can relate these power laws that I've shown you one-to-one with results from granular matter or something. So this really hard bookkeeping to do. Any search process, every fragmentation process is of sample space reducing nature. Now, if you the spaghetti problem, the spaghetti, you put a mark on the spaghetti, you break it, record the size of the spaghetti with the mark on it, the list, break it again, record the length again, and you do this until you end up at the spaghetti atom scale. And then do this many times, you get Zipf's law or a power law size distribution of the spaghetti, which is the same. It's not the same. Spaghetti is not a meteorite, but meteorites are typically part of bigger structures, and the measure of how these sizes are distributed, you can read off the moon craters.
In that sense, also self-assembly, when part of the cluster is also sample space reducing because they go and there are less and less clusters.
Yes, yes, and to work out the entropy of this, we did a couple of years of work into.
We should actually try to if you say like that.
Propagation of information maybe it's a sample space reducing process. Maybe that's too general of a statement, but if you're not producing sentences in a way that are sample space reducing, you're not conveying information in an efficient way. You can, of course, convey information, but maybe not efficiently. Games. Chess, for example, in the beginning, it's not sample space reducing, it's sample space expanding, but very quickly it becomes sample space reducing. That every move restricts the number of possible games, how you can finish it. And guess what? If you look at some statistics, you find Zipf's law in Go, you find Zipf's law in chess, and different aspects of it. Record statistics we talked about. Yeah, and of course, sequences in human behavior are sample space reducing. So across your life, as a baby, you can do everything. You can become a scientist or a piano player. And everything you learn reduces your Makes you more, you know, SOP.